Let's now see how to prove that the square root of a prime number is an irrational number. Before going to prove this, we need another interesting theorem. Let p be a prime number. If p divides a squared, then p divides a, where a is a positive integer. We are given that p is a prime number, a is a positive integer, and p divides a squared. Let the prime factorization of a be p1 times p2 times and so on times pn. Therefore, a squared equals p1 squared times p2 squared times and so on times pn squared. Since we are given that p divides a squared, by the fundamental theorem of arithmetic, we can say that p is one of the prime factors p1, p2 and so on pn. Thus, a equals p1 times, p2 times and so on pk minus 1 times pk plus 1 times and so on times pn. Therefore, p divides a. Prove that square root of 2 is an irrational number. Let's assume to that contrary that the square root of 2 is a rational number. So, we can find two integers r and s where s is not equal to 0, such that the square root of 2 equals r over s. Next, suppose r over s is not in its lowest form, that is, r and s have common factors other than 1. We can reduce it to the lowest form, say a over b, where a and b are coprime. Now, squaring both sides and cross-multiplying, we get a squared equals 2 times b squared. Thus, we can say that 2 divides a squared, which implies that 2 divides a by the previous theorem. As 2 divides a, we can write a equals 2 times c, where c is any integer. Next, on substituting a equals 2c in equation 1 and simplifying, we get b squared equals 2 times c squared, which implies that 2 divides b squared. Now again, from the previous theorem, we can say that 2 divides b. Therefore, from step 4 and step 7, there is a common factor 2 for both a and b, which contradicts that a and b are coprime, as in step 2. This contradiction arises due to our incorrect assumption that square root of 2 is a rational number. Hence, it is proved that the square root of 2 is an irrational number.
Like a Hellcat.